Welcome to Presentation 40. Today we're going to be talking about the Inertial Measurement Unit IMU system. I will be using the MPU 6050. Our Inertial Measurement Unit system belongs to our Layer 3 architecture. We're going to use the services from a number of items in Layer 2, especially the UART framework, I2 framework, the I/O ports, timer counter framework, and external interrupt framework. We're also going to use some of the services from our Layer 3, which is going to be our PWM Controller and our Servo motors. So let's go to the agenda. So today's agenda, first I'm going to go through a description of the system. Next, I'll show you the data sheet and we'll develop the framework. Next, we're going to review I'll show you how to put together the code to make everything play together. Next, we'll go through a sample program. And finally, we'll go through a summary. So let's start with the description. So I'm going to be using, as I noted, the MPU 6050. The MPU has an accelerometer and a gyroscope. The accelerometer measures acceleration in terms of G's on the X, Y, and Z axis. So we're going to be able to measure acceleration on the X, Y, and Z axis. Now the gyroscope is going to measure angular velocity. It tells you the rate of change of the angle. So basically it's going to provide the angular velocity here. Now let's look at the unit. So this is the MPU 6050, and basically we're going to communicate with the MPU through the I2C. So we're going to be connected to the SCL and SDA interface. And in the unit, it tells you this is the direction of the acceleration and also how the angular rotation. So when you install this, you get an idea how to install it. So let's look at some of the background information you need to develop the program, the theory. So here we have a vector of gravity. When everything's still, we have the gravity pointing down. Now here we tilted this surface. And what we're interested is in this angle. So we could say, hey, this is a pitch, an aeroplane going through a pitch angle, and we're interested to know what is this particular angle. So the accelerometer is going to give us the A sub Z acceleration on the Z axis and acceleration on the X axis. So we get that data from the accelerometer, and we have to figure out how do we get the theta angle. So if we look at this triangle, we see that alpha plus beta has to be equal to 90 because this is 90 degree. So we have alpha plus beta 90 degrees. On the other hand, alpha plus theta has to also be a 90 degrees. So by looking at these two equations, we figure out that the theta and the beta are the same value of angle. So now I also know that the tangent of this angle which is the tangent of this one, is equal to a sub x divided by a sub z. Those are the numbers that we get from the accelerometer. So then we can figure out the angle by taking the arc tangent, the inverse of the tangent and of AX divided by AZ. So now we have a way of figuring out the angle just by getting the acceleration on the Z and X values, coordinates. Now next, let's look at, so if this is the pitch, let's look at the roll. So we have here the gravity 1. And then when we do the roll here, again, we're interested on the theta angle. And we go the same way, but what we're going to get from the accelerometer is going to be the A sub acceleration in C direction, acceleration the Y, and with that information and the we can do the theta is going to be like I showed before as the inverse of the tangent of A sub Y divided by A sub Z. Okay, so now we figure out pitch and roll using the acceleration, but we also get the from the gyroscope, we also get the rotation velocity. So from the MPU, we're going to get the from the gyroscope, we're going to get the angular velocity that comes from the IMU, like I mentioned. Then the time is if we can measure the time between measurement, which we can, then we'll know the elapsed time. So we know the elapsed time, and we know the velocity. So the rotation angle is going to be equal to the angular velocity, which we get from the IMU multiplied by the time. So what it amounts to is we read angular velocity and we figure out what is the change in angle, and then we add or subtract from the current angle. So that's how we do that. So basically what I'm telling you right now is from acceleration we can figure out the pitch and roll, and also from using the gyroscope we can figure out the pitch and roll. So now the question is, why do we need both? So the accelerometer, it measures every vibration, even the tiny vibration. Very precise, but also very sensitive to tiny disturbance. So basically you have a good measurement, but the vibration is going to affect it. You're going to get a lot of data with a lot of spikes, for example, and I'll show you next. I'm going to show you how that looks. Now the gyroscope, it measures only rotation. So the new angle is going to be equal to the last measure angle plus the angular velocity times the time that has elapsed. Now the issue with the gyroscope is that it drifts over time. So if you have a small error in angle, as you integrate this, the error is going to grow and grow more. So what you have here is something that is accurate, but is affected by vibration. And you have another one that is fairly accurate, but it drifts away. So what do we do? So we're going to combine this information that we're getting from the two sensors to get a better result. And that's the way we do that. That's called the complementary filter. So the gyro short-term accuracy accelerometer can correct the drift of the gyro. So we put those together to get better data. So our angle is going to be 98% of the angle that we just calculated for the using the gyroscope. So it would be 98 times the current angle plus the change in the angle, and we're going to multiply that by 0.98. So we're going to use that data, 0.98 of that data, we're going to give it a weight. And then we're going to calculate the same angle using the accelerometer, and we're going to multiply it by 7.2%. So we're going to add a lot of the gyro and a little bit of the acceleration. And what we hope is that we're going to get something that is accurate and is not drifting anymore because it's being corrected by the accelerometer. So what I'm going to do here is I'm going to show you the output. I have a setup. This is a couple of servo motors, and it's going to simulate pitch and roll. And the output is shown here in this plotter. I'm plotting the data that I get. So you can see here, and you can see the vibration when this gets started. you can see how much vibration, and that's being reflected right here. That's in blue is the accelerometer, and now in red is the complementary filter. So you can see how the complementary filter got rid of a lot of the issues that we had with the vibration, and also so you're using mostly the gyroscope data, but we're correcting it using the accelerometer. So you can see again here the obvious the data, and how it gets rid of the vibration, and we can read the data so it's usable. What we had before, it wasn't. So now let's look at, this is the simulating the pitch. Now let's do the roll. So here you can see the same system, but this time we're rolling. And again, I'm plotting here both the, in blue is the accelerometer, and in red is the filter data, using the complementary filter. You can see how I got rid of the, I've only displayed the filter, complementary filter. You see how nice and smooth this curve is. And you can see, and so even though this is a fairly nice motion, still you can see how the vibration still is, you can see that the effect of the vibration here, and even though it's a very smooth, not too much vibration. So that's the whole idea. So we get gyroscope data, we get acceleration data, we combine them to get the best of each. So let's continue. So what we're going to do next is let's go to the data sheet. So we see where I got all the information. So this document is going to give you a lot of the information that you're going to need for programming the MPU. So let's go through some of the highlights. So first I wanted to show you, we have a table that contains a laundry list of all the registers that you may need for manipulating the unit or getting data from the unit. So here you have all the registers. Now, after that, another area of importance is what follows, which is the register description. For each of the registers in the table that I showed you, the document has an extensive explanation on how to set them up. For example, we have a section on configuration, and that's always important because the first step in every chip that you get, and as I've been explaining over and over, is we need to configure the unit according to the data sheet. Next, another area which is interesting or important to understand is, so we have the gyroscope configuration. So from this unit we're going to get acceleration and gyroscope information. So how to set up the gyroscope is going to be in this section. Then here we have how to configure the accelerometer. Now let's go to another page, 29. Here it shows us how to get all the data that we're going to need for the acceleration data. It shows you the register and other information related to the acceleration data. Then followed by the how to get the temperature data. And here we have on how to get the gyroscope data. Now, so basically, At this point, I've given you an idea of this document. It shows you where all the what are all the registers, and some of the registers which I consider to be most important that we need to understand up front. So anyhow, let's go back to the presentation and set up the framework. Okay, so let's go to let's set up the framework. So what I did here is from the document that I showed you, the data sheet. So I took the register address, description, and name, copy and paste that, and then next what I did, I created the code for representing all those registers so we can manipulate them as needed. So here you can see, and I create the framework, which is a include file. So you can see here the names and the number of the register. And basically, this is also a good way to trace where all this data comes from. It comes directly from the data sheet. So if you see in any documents, these names, you know where they came from. So we have our framework put together. And the next thing I'm going to do is I'm going to show you how we go about initializing the IMU. And let's go ahead and do that. So let's go through the code that is going to be required for IMU initialization. So what we're going to have to do is we have to power up the unit and wait for a little while. Next, we have to wake up the unit. We're going to have to enable the sensor. We're going to disable the FIFO and also reset the FIFO, the data to 0. Now let's see why we need to do that, but before, let's see what's the technique. So we have the delay, that's typical. So, but the first thing, we're sending this to the I2C. So that's something that we've seen many times. So we have to send the start command, then we send the transmit plus write and the address, and then the register where we want to write the data into and the actual data, and after that we do the stop. And then I waited 100 milliseconds. Yes, a little bit of give it time to do things. It may not be needed, but I went ahead and put it there. Now I'm going to do the same thing for all the different functions. So let's see what we do. So first we have the reset, which is basically sending the power management 1, the value of hex 80. And that all comes from the data sheet, of course. Next, we wake up the sensor, and again that's another message to the power management _1 with the value 01. Then after we wake up the sensor, we're going to enable the sensor. So that's going to be the power management _2 and the value 00. And then the next two is to disable the FIFO and the data inside the FIFO. And the reason we do that is because we're going to get all the data in real time. They don't have to store it for us to get it later on. So let's continue. Now here, what we're going to do is we're going to set up the low pass filter, the sample rate, the gyro range, and the accelerometer range. Now, as before, what we're going to do is we're going to use our I2C. So we send the start, the transmit address plus write, because we're going to write into the unit. Then we transmit the register where we want to write the value, and then we stop, and then we do this over and over. So let's look at each of the parameters. So first we have the set digital low pass filter. So we have three options. No filter, 3, which is a middle of the road, we could say a good balance, and then finally we have the very smooth but slower response. So what I decided to take the middle, which is value 3. So that's what we're sending here. And when we do that, basically what we're doing is setting the rate where it's going to go and read the data, internal data, to 1 kilohertz. Now, once we do that, the next step is we want to ask, okay, how often are you going to send it to us? So they get the data at one rate, and then the next questions are what rate they're going to send it to us. That it doesn't have to be the same. So what in this case, we decided to use this parameter equal to 4. You can see it right there. Now, by setting up this parameter to 4, which is the SMP LRT div, the formula for the output rate is going to be the internal rate, which we already set up here, 1 kilohertz, divided by 1 plus the parameter we selected. So if we put this into the formula, then it basically says that we're going to get our samples are going to be at the rate of 200 kilohertz, which is more than adequate for us. So I put a note here. So we selected DLPF, which is this digital low-pass filter, to 3. So that filters noise and set internal processing rate. So we have a rate. And then we set the SMPLRT div4 equal to 4. And that's how often data is going to be output to us. Next, let's set the gyro range. So what we did in this case, we said, hey, that's going to define the maximum rotating speed the sensor can measure. And we have to choose the smallest range without getting saturated, so it's supposed to handle. So we decided to use a plus minus 200 degrees per second. Now, that's something that you have to set for your unit, but at the rate we're doing, really, that's all we need. So now here I have a number of 130. That means that each number in the that is going to be outputted by the gyro is going to be 131 degrees per second. So, how did we get here? So we said the range of the is a 16-bit range of our MPU. So that can send a value as large as 65,536. So the total range is plus minus 250. That's 500 in the span. So if I divide 65,000 by 500, that means 131. So if the number I get, I need to divide it by 131 to get the degrees per second of rotation. So now let's look at we need to set the acceleration range and how big a force you can measure versus how precise the measurement. So I selected a 2G, plus minus 2G. Now going through the same rationale as before, we have the range is 65,536, and the for our maximum number that can hold the unit, and the spam is going to be it's going to be 4. So that's plus minus 2 G's. That's 4. So if we divide the 65,000 by 4, that's going to give us the value for 1 G, and that's going to be 16,384. So when I get a number from the accelerometer and I divide it by 16,384, that's going to tell me how many G's I'm getting. As when I divide it by 131, it's going to say how many angles, the value of the angle here. So if you look at the code again, this is similar. We do the start address plus write we want to configure the gyro, and then we just put the value we want. In this other case, we do the same thing. So we do the acceleration configuration, we set to 0. So that gives you all the configuration we have to do for this unit. So basically we set up ranges, we set up the rates, and then decided not to use the FIFO. We had to wake up the unit, and we have to enable an instrument. So with that, let's go back to our presentation. Okay, so let's continue. What we're going to do next is we're going to see what it takes to get all the data that we need for doing our calculation from the IMU system, using, of course, our I2C. So let's review the code that we need to get data from the IMU. So our connection to the IMU, as I've noted many times, is the I2C. So let's look at the code. I start by setting up a buffer of 14 parameters, and so we're going to have to get we're going to have to get the acceleration, which is 2 parameters on the x-axis, y-axis, and z-axis. That's 6 parameters. Then we're going to have to get the temperature. And finally, we're going to get the gyro data, which is going to be two parameters for the x, y, and z direction. Now, on the I2, what we do is we call out the first address, and then we continue to ask for the data, and it goes sequentially, so we don't have to write the data every time. So the first thing we have to, as usual, we start with the start, of course, TW I2C star. Then the first thing we have to do is we have to write to the IMU asking for the data. So what we do is we send the transmit address plus write, and then we transmit with the address of the IMU. And then we transmit the where we want to start the data to come from. The first address, which is going to be, we start with the acceleration x, and that's the most significant, the h. After doing that, so we just at this point we notify the IMU, hey, we want you to send me the following data. Then we do a repeat start, and then we do a transmit address plus read. That means we want you to send us the data. Now that's all I2C protocol. So I have a presentation I2C if you have any concerns of what I'm doing here. Okay, so now we have to get our 14 parameters. Now for every parameter that we get, we have to acknowledge it, except for the last parameter, where we sent a not acknowledge, means that, hey, we're done. So what we do is we do a do loop from I to 1. It's going to be from 0 to 12, and we are going to put that on the buffer 0 to 12. It says receive. We want to receive data with acknowledgement, and then so we do this loop and get the first 12, the first 12 parameters, and then after that we do this one more time for the 13th parameter, but this time we have to send it separately because we send a receive data with not acknowledgement. So at this point we have our 14 elements from 0 to 13, which is the 14 elements. So now we send the stop command, and now what we have to do is put the accelerometer on the X, Y, and Z. We need to put those two parameters together, the most significant and least significant, to create the actual acceleration. So the acceleration on the x-axis is going to be buffer 0, which I shifted left 8 places to make it the first most significant bits, and then after that I ordered with the next parameter, which is the least significant. So I do that for the x, y, and z. Next I get the temperature, which again, what I always have to do is the most significant part of the message has to be shifted 8 left, and then we order with the least significant. After getting the temperature, then we get the gyro x, y, and z. I mean, I put together the parameters for the x, y, and z values. So this shows you how to go ahead and get the data from the IMU. So basically, you transmit a plus write with the address and where you want to start reading, and then you transmit the plus read with the address and start reading the data. Now the next thing I want to look at here is the calibration. So what happens is, when you put the sensor at the start with no motion, everything should be 0. But in actuality, everything is not 0, because your system is not perfectly on a level. So you always have a little bit of the acceleration, the gravity vector, a little bit tilted, just a tiny bit. So, or not. But what you want to do is, you want to, with no motion at the start, you want to see if there is you need to do any calibration. That means that it doesn't mark 0. So what we do here is, first we say, hey, our sample, I'm going to do this 800 times, and I'm going to average. It should be 0. If it's 0, great. If not, that's a parameter, a number that I'm going to have to subtract from every parameter. So this is how I start. I go from 0 to number of samples, and then the first thing I do is I read the parameters. Then I add the x, y, and z, and I continue to do this for 800 times. So I have a large sample. Now what I want to do is I want to get the average, and that's going to be my offset, if any. So I take the sum of x, which were the sample of 800, and divide it by the 800, and that's going to give me my offset for x, offset for y. And now the offset for z, it's a little bit different. So the z parameter should be to start 1G. So when the thing is no motion, it's just sitting there, I should be reading 1G. So now let me explain a little bit here where this 16,384 comes from. So we have a 16-bit word where we're going to store our data for each of the parameters. So that's 65,536. Now I'm interested in the value of 1G. Now when we initialized our system, it was plus and minus 2G. So that means that would be, I need to get this whole parameter and divide it by 4 to get the value for, that would be for 1G. So what I do here is, once I've calculated and divided, what I should have is 1G. So in theory, if I subtract it from 16,384, which represents 1G, I should get 0. If not, well, that gives me the offset that I need. Okay, so the resolution of the IMU is 2 to the 16th, which is 65,536. the resolution for our G's is we should be able to sense plus or minus 4G. So this number represents plus or minus 4G. So if I want 1G, then I have to divide it by 4. So there we have the calibration for our accelerometer. So once we calculate each of these items for the acceleration, we're going to have to subtract a number if it's not quite 0. So next, let's look at the gyro. For the gyro, we're going to have to do the same thing, and I did again for 800. Now 800 is just a number that I picked just looking at other programs and whatnot, but you can always play around with that number. So what I do here is, again, I go from I to the sample, which is 800. Then first thing is I read the data. Then I start adding the gyro, the X, Y, and Z. So once I completed adding this, then what I'm going to do is I'm going to get the average. So I get the gyro offset and the sum divided by the sample size. So what I'm going to end up, the gyro X offset is basically going to be the value of the average if the parameters are not 0. So these parameters should all be 0, but because I'm just seeing what I think is the correct position, but if not 0, that means because I probably have physically some kind of a tilt on my instrument or whatnot. But this way I can calibrate every time I get every time I read a sample from here. The first step I do is I subtract the calibration parameter. So with this, we can continue with our presentation. Okay, so now we have the data. Let's do some of the calculations of the angles. So let's look at the code that is going to be required to calculate the angles, which is the pitch and roll. So let's look at this figure to see what's the theory behind it. So we have a going straight and level, the gravity is pointing down. Now what we're interested in is if this we're interested in finding out the pitch angle. So what we want to do is calculate the theta. Now we know that alpha plus theta is equal to 90 degrees. And we also know that Bravo plus alpha is also 90 degrees, which means that theta and Bravo are equivalent, are equal. So to calculate my angle theta, what I need to do, I know that the tangent of theta is going to be equal to AX divided by AZ. So now I have this equation of the tangent, but what I'm interested in is in the angle theta. So the angle theta is going to be tangent to the -1 arctangent of AX divided by AZ. So next, let's see how we calculate the roll. In this case, this is the roll. And basically, again, we looked at the figure and we know that alpha plus theta is going to be equal to 90, and alpha plus Bravo is going to be equal to 90. So the tangent of this angle is going to be equal to A sub y divided by A sub z. but we're interested in the angle. So the angle is going to be equal to tangent of to the -1 of AY divided by AC. Now the AY and AC, those are parameters that we get from our IMU. So the AX, AZ, AY, and AZ are going to be provided by the IMU, and we have to do the inverse of the tangent of these ratios to get the angle. So let's see how we do that. Let's look at the code. So we have a routine which is accel pitch roll underscore angle. So first thing we do is we get the AX. So the AX is going to be at the ACCX, which is the data we get from the IMU. We subtract the offset, and then we're going to divide it by 16,384. That's just to put it in terms of G's. Next, we do the same thing for the AY, which is going to be, again, the acceleration on Y minus the offset, and that's again divided by 16,384. And finally, we do that for the AZ. Now, let's get the first angle X, which is going to be the pitch. So we're going to do the arc tangent 2, that's the inverse of the tangent of the, I'm up here actually, I'm doing the roll first, sorry. So for the roll, so it's going to be AY divided by AZ. Now this is going to give me the angles, but the angle is going to be in radians, and I want it on degrees. So what I'm going to do is I'm going to multiply it by 180 and divide it by pi. Now for the pitch angle, I'm going to do the same thing, which is going to be arc tangent of minus x. But in this case, I use the square of a sub I and a sub z, and then that's going to give me my angle, and then I multiply it by 180 and divide it by pi. Now I use these particular functions instead of this one, which is, I should say this one, which is simpler. And the reason is because in the literature I've read that this works much better. So I went ahead and did a try, and it seems to be working okay. So I just wanted to show something different. So let's continue. Now we're going to do the same thing for the gyro, for the pitch and roll. So we know that the rotation angle is going to be equal to the angular velocity times the time. So yes, that's velocity times time, and that gives you distance. Now the delta time is going to be just the time between measurements. So I read something, then I read it again, and then I figure out how much time has gone by. And the angular velocity, of course, that comes from the IMU. So the rotation angle, so this is the delta rotation, but the overall rotation is going to be my my current rotation plus the delta that I just calculated here. So that would be total rotation plus angle velocity times time. So that's what I was doing here. Now another piece. So I'm giving you just different pieces of data that are going to come together when I talk about the code. So the ADC of the MPU is 16-bit resolution, which means that it has 6,535. You can hold that number. Now, when we configure our gyro, we set it up to be plus minus 250 degrees. So that means that each degree of rotation is going to be 131.7, which is basically dividing the 65,553 by 500. So basically, this is what I show you is how you calculate the change in angle, how you calculate the whole angle that you have, and then how you convert it to degrees. So let's look at it. So pitch and roll angle. So first I do is I get the delta time. And then I say, okay, so I have my overall roll. No, I'm sorry. First I have to get rid of the offset. So I take the parameter, subtract the offset, and divide it by 131, and that's going to give me in terms of degrees. Now I do the same thing for the y. I take the gyro y, subtract the offset, and divide it by 131. So now let's calculate the actual angle here. So what I'm going to do is I'm going to take the current angle, and I'm going to add the delta that we just changed. So we have the gx, which is the change in degrees times the time elapsed, the velocity of change times the time, and I'm going to add it to the current angle, and that's going to be me the increase from the last point, or decrease. And then I'm going to do the same thing for the y. So one is taking care of the pitch, and the other one is taking care of the roll. So in a nutshell, what I do is I get the current velocity and multiply it by the time. That gives me the space, and I add that space to the current angle, so that increases or decreases the angle, and I do that for pitch and roll. So now let's look at the delta time. So what I'm doing here is something that I've showed you in other in the timer presentation. So I read the time. Okay. Then one of the things is as I read the timer is going to get to a point where it's going to roll over, and that's 65,536 because I'm using the 16-bit timer, so I have to account for that. So what I do is I subtract the current time from the old time, and that gives me the change in time, and that's what I'm going to have to use. That's what I need for my program. Then the old time becomes the current time, and then I convert the time, which is this far, everything is in ticks. At this point, I convert it to seconds by dividing it by 5,625, and that's what I send back. So what this is doing is I get the current time, I save the old time, so then I subtract it and I get the delta time, and that's what I provide for the gyro pitch and roll angle. And what they do is they use the delta time, which is the time that has elapsed since the last time I read it, and multiply it by the angular velocity to get the space which gets added. So with that, let's see, we have one more calculation to go. So now we have our angles, changing angles for pitch and roll using the gyro. We have the change of angles for pitch and roll using accelerometer. So what we do, we want to create an equation that takes in these two parameters and combines them in such a way that we can get the best possible result. So how we do that? So we know that the gyro angle is actually pretty accurate, but with time it shifts. It keeps keeps wandering. So what we're going to do is we're going to say, hey, 80% of the time this is correct, but as it starts shifting away from where it should be, I want to bring it back. So what I'm going to do, I'm going to use the accelerometer parameter to bring it back. So I'm going to take my data of the gyro and say multiply it by 80%, and then I'm going to use the accelerometer data multiplied by 20%, and that gives me my 100%. And it's so I've taken the best from the gyro and the best from the accelerometer, because as you know, the gyro drifts away. So as the gyro starts drifting away, I want to bring it back, and so I use the accelerometer to bring it back. So that's called a complementary filter. So this is what I do. So I have the angle plus the change in angle. So what I'm doing is I just incrementing the gyro. But I know that this parameter is correct, but it's drifting. So I'm going to say I'm going to give it a weight of 98.98, and then I'm going to use my accelerometer, which I know is correct, but the problem with my accelerometer is sometimes it's too jumpy. The noise affects it. So, but I could say that if I use it 0.2%, most of the time I'm going to get the correct value. So that's what I use. In this case, I'm going to call gyro angle. This is going to be for my rolling, and this is going to be for my pitch angle. So I correct for rolling angle, and I correct for pitch angle. And we'll see when we run the program, you're going to see exactly how this works. And I think I've noted before, so you kind of get a good idea why we do this. So let's go ahead and continue with our presentation. Okay, so let's continue. So now what we're going to do is put everything together in a sample program. So let's look first about how we're going to put the system together. So we have the ATMEGA 328. It's going to be, we're going to connect it to the SDA and SDL because we're communicating to the I2C. And the same thing goes with the accelerometer and gyroscope. The MPU 650 is also going to be hooked up to the bus. So this is fairly simple, clean installation, the way these two get connected. So what we want the program to do? First, we want to get the acceleration data for the X, Y, and Z axis. Next, we want to do the same thing for the gyro data. Once we get those parameters, we want to calculate the calibration parameters. And once we've figured out what are the calibration parameters, then we want to calculate pitch and roll. Now with those, once we get the pitch and roll, we want to use that data to calculate our complementary filter to get more precise pitch and roll angle. After doing that, we're going to display the information in the serial plotter application. So it's time to put everything together. So let's continue. But before we do that, I think I'm going to talk about the test setup. So we have a little test setup where we use a couple of we use a couple of servos to create the motion to see how things behave. So let's look at our test setup talk a little bit about that. So I'm going to show you the test setup so you can get an idea how we get our data to verify that the roll and the pitch are working okay. So what we have here is the IMU unit is going to go up here and it's going to be controlled by this microcontroller. And then we have an additional microcontroller that is going to control these two servos to do the pitch and roll. So let's see how this works. So here you can see the pitch. So the servo motor just goes back and forth, showing the output from the IMU goes to the serial interface USB to this program, which is a serial plotter, and you can see here the output of the signals. And we have to put this in certain format that I'll show you once we go through the code. And the main program actually does that. So let's look at the, so this is doing the rolling. So let's look at the pitch control. So this is doing now the pitch. And you can see here the signal. And so before we were actuating this servo, now we're actuating this servo below. So it just goes up and down, and you can see the output. So I can control the output of the serial by enabling or disabling the input. And in this case, I'm enabling, disabling the raw vibration opposed to the data that is filtered. So you can see that. So anyhow, this gives you a good idea of what we're using for programming for testing our system. Okay, so let's look at the sample the code for our sample program. I like to show you the whole program together. So let's go ahead and do that. So let's go ahead and review all the source code for our program. So I've already gone through many of these items, but I just, at the end of the presentation, I always like to show the complete program and the output. So we have here a routine for initialize the timer, which we use to calculate the data for the angle for the gyroscope. We have the init I square C, the start, I square C start, and I square C repeat start. Now these three items, the start, repeat start, and the init, those are cut and paste from my presentation that I did on the I square C. Nothing has been added for this program. In the initialize timer, the same thing. If you go to the timer routine, you'll see timer presentation. You see it exactly. I did the same thing here. Next, we have more of the I square cut and paste, I call it. The I square C stop, transmit data, receive data, transmit plus read, transmit plus write. So the important thing here is that for this program we have to do nothing for those. It's just cut and paste. So if you have any concerns about the I square C, you have to go to the I square C presentation. Next, now we have here the items that are specific for the MPU. So we're going to configure the MPU like I already showed you. Now this is new. Who am I? So what it amounts to is when we completely doing the initializations, we want to make sure we didn't break anything. So what I do is I send the who am I, and there is a very specific reply from the MPU if everything is okay. So what we do here, I square C typical, we do the start part right, then we send the who am I, which is what we want to get a reply from. So we send that to the MPU, and then let's get the reply. So we do a repeat start, we do a I square plus read, and then we get the data. Now the data, we use the receive routine, but we have to make sure that this we say not acknowledgement. We're getting one message, which is the final message. So when you send the not acknowledgement, means say, hey, send me the message, and this is the last message I'm getting, so I don't need to acknowledge. then you do the stop, and then what we are going to do is we're going to display that the value in the input data on the laptop. We do here the serial integers, parse, and then we do a couple of serial 0. And the reason is because the software on the plotting software requires us to have some format, which is just the number, comma, the number, and then we do the return. So we have a routine to do the read all, which is going to get all our data that we need to do all our calculation for pitch and roll. Next, we have a calibration for the accelerometer. And after we've done our calibration, then we can go ahead and do our pitch and roll calculations. Now we have a routine here to do the get delta time, which basically what it does is just gets the time so we can use for calculating the gyroscope angle. Now we have a routine here to calibrate the gyroscope, and then we have a routine to calculate the gyro pitch and roll angle. Now the last routine before we get the main is I call it the stable pitch and roll angle. So that's where we do the equations, where we use a little bit of the acceleration, a whole lot of the gyroscope to get our final angle. Now one of the things that we have to realize is that when I do the stable calculation of stable angle, I call it here the gyroscope X and gyroscope angle Y. So it's same numbers of the gyroscope, but this represents the stable angle. So I did that because that was easier for me to go ahead in the equation, a shortcut. So hopefully it's not too confusing. So we got to the main program. So we are going to initialize the UART. We're needed to send the data to the laptop. We need to initialize the I2C, which is the bus we're using for communicating controller and MPU. We need to initialize timer because we're going to use the timer to calculate the delta time needed by the gyroscope. And then next what we do, we configure the MPU 6050, and we calibrate the accelerometer and calibrate the gyroscope. It's important that the system be resting while we do the calibration. Now, after doing all those things to make sure that we didn't break something, we send the who am I, and that's going to display a number. So now let's see what we do with the on the while loop. So first thing we read all the parameters. Next we calculate use the accelerometer to calculate pitch. We use the pitch and roll, I should say. Then we use the gyro to calculate pitch and roll. Next, we used what we got from these two routines in the equations that we call the stable pitch and roll angles. That's going to be the calibrated complementary filter, I should say. So calculate acceleration, calculate gyroscope, pitch and roll, and then we use the complementary filter to get the best we can. Now, on the output of the routine, what we're going to see is we're going to see the raw acceleration. Next, we're going to see the acceleration for pitch, and we're going to see acceleration for roll. And then we're going to use see the output of the complementary filter for the pitch and for the roll. And then we wait 10 milliseconds, and then we do this over and over, so as the thing changes. So let's look at the outputs. So what I did here is I went ahead and just showed you the output from the laptop so we can see that a little bit better, because if I show the whole setup, it's kind of small. So let's look at it straight from here. So now the blue portion is the output from the accelerometer. You can see as my set shook up, that created a lot of noise. In red is the output from the complementary filter. So you can see here, and the complementary filter is much nicer. The output is more readable, I should say, opposed to nicer. So let me see if I can. So this shows you the very the lines from the complementary filter. So it's much easier to read. It's not affected. So you can see here, I go ahead and added the the filtering, and then removed it, so you can see the output. So let's look at the other one. This is the one from the for the roll. So in green is the complementary filter, and in red is the output from the directly from the accelerometer. So you can see here the difference. So this is much nicer. So you can see how it eliminates completely not completely, but it makes it something that you can actually read, and not all the distortion that you get from only the accelerometer. And another thing is that we're not getting the drift from the gyroscope. So we're eliminating the drift from the gyroscope, and we're eliminating all the vibration from the accelerometer. So I think this gives you a good idea of what they mean when they say with the accelerometer you have a lot of noise, because if the system shakes a little bit, that's going to be reflected in the accelerometer, and then you get an idea of how nice the output is from the gyroscope, except that the gyroscope with time it drifts. So basically, when you do your you're starting your system, you always have a little bit of a problem with the angle. Yes, a very small failure, not failure, it's inaccuracy, I should say. And then as time goes up, that time goes by, the inaccuracy increases. But then that's why we use the accelerometer to get rid of that drift in our complementary filter. Okay, with that, I think we're ready to continue with our presentation. Okay, so let's go ahead and continue, and we finally got to the summary. So today I gave you a description of the MPU 6050, and next we went through the data sheet. After looking at the data sheet, we created our framework. Next, I went and showed you how to go about developing the code, all the different parts of the code. And finally, we put everything together on the sample program. So I hope you've enjoyed this presentation, and thank you very much for taking the time to spend with me. See you in the next one.